Well, hello and welcome to Chapter 7. This is going to be hypothesis testing. Now, pretty much the rest of the course that we would do is going to involve testing of some kind. And this is really gets into real world statistics, and it's what everybody uses to determine whether or not something works. Now, we've used confidence intervals in the past to talk about where we think something is, but in the world of statistics, a hypothesis test presently is kind of what's expected. And ultimately, it kind of gives it gives a yes or no answer. It doesn't say, it's about here. And that's really what a hypothesis test is going to get at. Okay, so we're going to use some sample statistics to make a claim about a parameter. And we're either going to say, yes, it's true, or no, it's not, or we don't have enough evidence to support it. Okay, so for instance, maybe we might say that a manufacturer is going to advertise that the new hybrid car has a mean gas mileage of 50 miles per gallon. Now, we think that maybe it's not. How would you go about showing that that advertisement is false? Well, you could collect a lot of data and you could make a confidence interval, but ultimately what we kind of get at is in the world of statistics, what's more accepted currently is a hypothesis test. There is a little bit of a push to make confidence intervals a little more mainstream though. So what we're going to do is we're going to make a statement about the population parameter. In this case, we're going to be talking about the mean. Remember, the parameter comes from the population, so we'd be talking about mu in the case of the average gas mileage. And our hypotheses, there's going to be two of them. There's going to be one of them that represents the claim, and then the other one that is the opposite. So that only one can be true. There's no wiggle room where they might both be false or they might both be true. Okay, we can't do that. Okay, so when one of the hypotheses is false, then the other one has to be true. So that's why we have to be very careful about how we word our hypotheses. Now, this right here, this H sub 0, it's read as H null, the null hypothesis, or H naught. Okay, any one of those is how you might read it. And it just means that it's the initial hypothesis. Now, the alternative hypothesis, H sub A, or sometimes people just call it HA, or the alternative, H sub, whatever it is, this ultimately is what is going to be true if you determine that the null is not. So again, it's got to be very careful wording, and we're going to be very careful with our signs. If we use a less than or equal to sign on our null hypothesis, we can't use a greater than or equal to sign on the alternative. If we use less than or equal to, we have to use greater than. Okay, so you just gotta watch out so that these are exactly opposite. All right. Now, typically we're going to always make the null hypothesis the one that includes whatever value it is. Okay, so keep that in mind. I've seen it done other ways, but this is how what we're going to go with to be consistent with our textbook. Okay, so the equal sign will be in our null hypothesis whenever we're starting out with these. After that, we're going to be examining the sampling distribution in order to determine whether or not we think something is true or not, if there's evidence to support that it's not true. Okay, so here's a nice little table. This is from your book. This just deals a lot with the wording of things. You guys can pause here and read over it, but this is really just changing English into math statements. I'm not going to go through all of these. Okay, let's look at a couple examples now. We're going to write each claim as a mathematical sentence. That means using some symbols. We're going to state the null and alternative hypotheses, and then identify which represents a claim. Okay, so this is going to be very important for later on to make sure that for some other stuff we're going to do. So figure out which one is being claimed. In this example, a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Okay, so let's think about what we're going to be doing here. We can see that it says involved in at least one. Okay, so remember that we are going to have our null hypothesis be the equality. Now, oh, you know what? I said it in at least one extracurricular activity, but I fell into a trap right there. This is only referring to the extracurricular activities. It doesn't actually reference the proportion of people. They are specifically saying is 61%. And that, folks, is why I write down my answers ahead of time. So the thing we need to focus on here is that they're telling us it is 61%. Now, if our null hypothesis is that it is 61%, think about what the opposite, what the logical opposite of is 61% is. Is it less than 61%? Is it more than 61%? Is it not 61%? Yes, that's exactly what it is. It's not 61%. And we do that just by putting an equality or an equation sign, putting a slash through it. Okay, so this would be our null hypothesis, okay, that the true proportion, and we are using P because we're talking about the true proportion, not just from a sample, but our claim is that true P is 61%. Then the alternative, if we figure out, if our information leads us to believe that it's not 61%, then that's what we would ultimately conclude, that it's not 61%. Okay. The claim then, of course, in this case, is the null hypothesis. That's what the school is claiming. Okay. The next one, write a claim as a mathematical sentence. Again, same thing. Car dealership announces that the mean time for an oil change is less than 15 minutes. Okay, now a couple things. First of all, we're talking about the mean time. That means we're going to be using mu this time because we're talking about mean. So let's talk about mu, right? So the two ideas that we have going on here is we can either say that mu is less than 15, or therefore mu must be greater than or equal to 15. Now, these are the two statements that we're going to be using. We have to decide which is which. Okay, so we can very easily identify what the claim is, right? It says that a car dealership announces the mean time for an oil change is less than 15 minutes. That must mean that this one is the claim. That's what they're stating. Then we said that we're going to, especially as we get going on these, we're always going to let the one where it's equal to, that's going to be the null hypothesis. Mu is greater than or equal to 15, that must be the null, and then therefore this must be the alternative. Now I'm going to show you the typed version of that just so that it's a little bit cleaner. You can see here we have our H null is mu is greater than or equal to 15 minutes. Our alternative is mu is less than 15 minutes, and of course this is our claim. The next one, a company advertises that the mean life of its furnaces is more than 18 years. So once again, we're talking about the mean life. The meaning of life? No. Mu, that's what we're looking at here. So we're going to be writing some things about mu. We can say that its furnaces is more than 18 years. So one of these is going to be mu is greater than 18, and one of them will be mu is less than or equal to 18. Okay, so this is more than, that's an exclusively, or it's exclusive language, right? It's greater than. So these are the two ideas. We can see here that this one is the claim. And then we're going to use the one that is the less than or equal to in order to be the alternative. Okay, or I just said that backwards. No, I didn't say it backwards. I just haven't finished it. So then because this is less than or equal to, this is the null, and this is the alternative. Okay? So, and then typically what you'll see is you'll always see this written in order here. I'm kind of doing this over to the side to get my thoughts in order, and then I would come around, I'd write my null hypothesis here on top, and then the alternative after that one. It's probably a little bit nicer way of doing things. So here's one more for you to do. There's not really a context to this one, so this one's a little bit quicker, but it's a good idea to pause the video, go ahead and write the complement. Really, these are just using symbols, and this is number 12 from what would be your textbook or your homework assignment. So this would be number 12. Okay, so pause and try. So here's what we've got. We have mu is less than 128. That was the given. Therefore, that's our claim. And then if we have a less than, then our other one is going to be greater than or equal to. And because that one's the equal to, that's the one that we'll use as our H naught or the H null. Okay, so here is what these would look like using symbols. And since there is no context, that means we're done. Okay. All right, next, there's something called errors. Now, errors, just like before, whenever we were talking about our confidence interval, we were talking about maybe like a sampling error. Well, error doesn't mean you did something wrong whenever we're doing tests. It just means that you got the wrong outcome because of the data, because of your sample, right? It does not mean you did something wrong. Every time you do a test, okay, we always start with this notion that the null is true. Just start with that idea, right? The equality condition, start with the idea that that's true. Then, after we do our test, only one of two things is going to happen. You can either reject the null or you fail to reject the null. Now, this is actually pretty important language, fail to reject the null. We'll get into this a little bit more later on, but you either reject the null and accept the alternative must be true, or you fail to reject the null. Okay? Now, that's it. Those are the only two things that can happen whenever we're doing these tests. Okay? We don't get an interval and say, hey, we think it's somewhere in here. No, it's like it's black and white. That's pretty much all we get. And that's one of the nice things about a test. Now, the errors that could happen, they might look like this. So let's say that, in real life, the null statement is true. Now, we pretty much never know that. Okay, we'd always just kind of assume. But let's say that it is definitely true. And you go through and you do your test and you figure out that you can't reject the null. Then you have made a correct decision. Okay? But let's say that it's true for, like, you go and you do a census, you collect all the data and you now know it's true, which pretty much never happens. But when you took your sample led you to reject the null. You said, hey, I have evidence stating that the null hypothesis is not true. And so therefore I'm going to reject the null. Like you do your test and let's say you reject it. But you come to find out later on that it really was true. Then you have made a type 1 error. It's not that you did anything wrong. Your sample just led you to reject the null. A type 1 error happens whenever you reject the null, but you shouldn't have rejected the null. Now, a type 2 error is actually just kind of the opposite. A type 2 error happens when you fail to reject, and that's actually how I remember it. A type 2 is when you fail to reject, right? So kind of keep that in mind. This is the word to. When you fail to reject the null, but you should have. In other words, your data didn't give you enough information that would cause you to reject the null. But again, the only way to know this is if you do a whole census, and that doesn't usually happen. So type 1 errors and type 2 errors happen. They happen all the time. To be honest, most of the time you never know if you made a type 1 or a type 2 error for sure. Only if you've done a lot of follow-up tests or if you do a census and actually collect all the information. Now, these errors have different levels of consequences depending on the problem. Sometimes a type 1 error is worse, sometimes a type 2 error is worse. Let's go ahead and take a look at an example of this. So the USDA limits the amount of salmonella contamination in ground beef to 7.5%. A meat inspector, he can't inspect every single piece of beef that comes off the line, so instead they take a sample. So what he would do is take a sample and then run it through his test. So we're going to perform a hypothesis test to determine whether or not the meat inspector's claim is true. And then we've got to determine which error could occur and which one is more serious. All right. So our null hypothesis is that P, because we're talking about a proportion this time, right? It's a percent. Let's go back and look at it. It says that it's the limit is 7.5%, and when you see limit, that must mean it's going to be less than or equal to 7.5%. Since we're talking about this percentage, then we're talking about a proportion, hence P. So that's where we get this P is less than or equal to 0.075. Okay. Now the alternative is that the true proportion is greater than 0.075. And that's what the meat inspector was claiming. He was saying, hey, this meat is bad. It has too high of a contamination rate. Okay, so here's our null hypothesis and the alternative hypothesis, and this is what the meat inspector claimed. Now, anytime you do a test, it's possible to make errors, the type 1 and the type 2 errors. So let's see what could happen. Remember, a type 1 error is when you reject the null, but you shouldn't. So that's what a type 1 error is. Think about what that is. When you actually reject the null, but you shouldn't. That means you're saying that the true proportion is higher than 7.5% when that's not actually true. Okay, that the actual proportion of ground beef is less than or equal to 0.075, but you reject it. Okay, now it's the same thing I just said, it's just worded differently. Okay, so you are saying that you're saying that the true contamination is very high when in actuality it's not. Now let's think about what a type 2 error would be. A type 2 is when you fail to reject, but you should. A type 2 error is failing to reject this when it's false. Right? Maybe the evidence that you get doesn't actually cause you to reject this. So what happens? Well, if that's the case, then the actual proportion of ground beef is more, but you didn't really reject it. Okay? So that means that it has a very high contamination rate, but you didn't reject it. I hope I said that right earlier. Okay. So let's think about which of these is worse. Like what are the outcomes here? Okay, so when you run your test, if you make a type 1 error, oops, I went ahead. In this case, if you had made a type 1 error, like your data caused you to make a type 1 error, but again, you wouldn't know that it's an error. You wouldn't know that you messed up. You're just making a claim. You're running the test. Then the actual proportion of beef that's contaminated is less than this, but you reject it. What that means in real life is perfectly good ground beef you are saying is bad. The ramifications of that is you could cause a scare. You could cause a scare in a whole community if you could hurt local farmers, right? You could cause people to lose a lot of money on ground beef because they're going to have a recall on beef and on beef that was perfectly fine. So that would be the ramifications of a type 1 error. Making a type 2 error, failing to reject the null when it's false, right? Failing to reject when you really should reject it. What that would mean is that the true proportion of ground beef that has salmonella is higher than this amount, but you didn't get enough evidence to support it. So in other words, a really high proportion of ground beef truly does have salmonella and it's out there, but you didn't catch it. So the ramifications of that is that a lot of people could get sick and possibly die. Okay, you wouldn't do the recall. And so in a case like this, a type 2 error would be much worse. Death is worse than losing some money. Hopefully we all agree with that. Okay, so it just depends on the scenario, and it takes a lot of practice and a lot of examples in order to figure this kind of stuff out. Let's look at page 360, number 32. This says that we have to describe a type 1 and a type 2 errors for the hypothesis test of the claim. An urban planner claims that the noontime mean traffic flow on a busy downtown college campus is 35 cars per minute. That's the claim. So let's look at this. We said that if that's the claim, then we're saying the mean is 35 cars per minute. So a type 1 error would be when you reject the null, but you shouldn't. In other words, you say, no, the mean is not 35 cars per minute, when in actuality, it really is. Okay, that's what a type 1 error is. A type 2 is when you fail to reject. Okay, it would be when you don't have enough evidence. Okay, when you fail to reject the null. That is essentially whenever the noontime traffic rate is not 35 cars per minute, but you didn't reject it. Your evidence didn't say, hey, we have to reject this. That's what a type 2 error would be in this scenario. Now, just like whenever we would make our confidence intervals, we had to talk about how confident we were in doing this. We do the same thing with our testing. Like, how sure do you want to be? And you can think of these like confidence intervals. So we're going to, the maximum allowable probability of making a type 1 error is alpha. Okay, so if you see an alpha of 0.10, that means 10% of the time you're going to make a type 1 error. If you use an alpha of 0.05, and like these are all really common. If you use an alpha 0.5, 5% of the time you will make a type 1 error. An alpha 0.1, 1% of the time you will make a type 1 error. You can often think of this kind of like confidence intervals. When you use alpha 0.5, it's kind of like being 95% confident. It's not exactly the same thing, but it's pretty close. Okay, there's some, anyways. So depending on the importance of what you're doing, you might use different significance tests. If it's life and death, whether or not you make a type 1 error, then you might want to use alpha 0.1. Okay, if making a type 1 error could cause death, then you want to use a pretty high alpha, or I'm sorry, a pretty low alpha. Okay, so you just kind of got to think about what you're doing and decide what level of significance you need. Now, the probability of a type 2 error, we use this funny looking b. This is a beta. It's a Greek letter beta. And this is a lot harder to calculate. There's some other stuff with it. We can't just say like, oh, well, if this is 0.5, then that makes this something. Like it's different. So we're not going to be doing that anytime soon. Don't worry about it. But that's the probability of making a type 2 error. Okay? And then it also relates to the power of the test. If you are doing this for a company, if you're doing this for medical research, you have to state what the power of your test will be in order to determine whether or not your test's any good. Okay, so with these tests, this is kind of the order of things. After you state your null and alternative hypotheses, okay, then you take your random sample from the population and you calculate your sample statistics. Then you're going to compare that with your parameter in the null hypothesis. Okay. Then we're going to assume that the null hypothesis is true, and we convert everything to a standardized test statistic. The ones that we've done is we've done z's and we've done t's. This one right here, this x, depending on what class you're in, I guess, or what you have done, this is this. I know a lot of you out there right now are saying, oh, chi chi, right? No. And then some of you are like, haha, silly. It's actually chai, like my chai tea latte. I'm going to go get one of these, right? No, that's not right either. This is actually kai, like a K, K-I, chi. This is a chi squared. And so this is just another distribution depending on whether or not you covered it. I just wanted to throw that in there so that you're not reading it as x squared. This is a chi squared. Okay, then we use that standardized test statistic to make a decision about the null, whether we can reject the null or whether we fail to reject the null. Here's the instances where you would use those. If you're using the population parameter of mu, then we would use our z's or t's. And again, that just depends on whether or not you know the standard deviation or if it's unknown. Again, in real life, unknown is probably a little more common. Then for the population, if the population parameter is a proportion, that's a lot of p's, we'd be using p-hats, and that's our z's. Okay, and then you may or may not have covered this. The p-value, the probability value, that's what we're going to compare with our alpha value. Okay, that's what we're going to compare with that. And if the null hypothesis, this is the probability if the null hypothesis is true of obtaining a sample statistic with a value as extreme or more than the one determined from our sample data. Now I know I just read that out loud, but that's the likelihood of getting the number we got that extreme. Okay, and what we're going to do is we're going to compare that number with our alpha. We have three types of tests: left tail, right tail, two tail. Okay, and it depends on the region as to when you're going to reject. The region is indicated by the alternative hypothesis. So let's take a look real quick at what that might look like. Okay, if your null hypothesis is mu is greater than or equal to k, your alternative is mu is less than k, and you end up getting a p-value somewhere down here in this region, okay, then that's whenever you would reject the null. If you get something that's this far or further, right? If we were using an alpha 0.5 or an alpha 0.1, whatever this is, if you get something past that, that's down here, and that's what would cause you to reject the null. Of course, you also have right-tailed, okay, if you're looking for something greater. And then we also have a two-tailed test, and this is what you use whenever you say is not, right? We did one of those earlier, like mu is equal to something. The alternative is that mu is not equal to something. Okay. So let's take a look here, and we'll go ahead and draw a picture of what this is. So a school publicizes the proportion of its students who are involved in at least one extracurricular activity, 61%. Right? This goes back to what we did earlier. Here's what those looked like. We said that our null hypothesis, or the original, it was that the true proportion is 61%. The alternative is not 61%. Okay, and then this is the mathematical symbols, if you will. This is the English language. Look how much shorter this is. That's why mathematicians use symbols all the time that make so many people mad, because they're like, oh, I don't like your shorthand. But look how much quicker that is. Now, what this would look like in terms of a picture will be this. Because we want the not equal to part of this, it's going to be a two-tailed. Okay, and if we were using an alpha, of 0.10, then the area of these would be total of 0.10. In other words, half that value. Okay. All right, let's go ahead and look at another one. We're going to state the null and the alternative in words and in symbols. Determine which hypothesis test is left-tailed, right-tailed, or two-tailed. And then we'll explain our reasoning, draw a quick sketch. A manufacturer of grandfather clocks claims that the mean times in its clocks is no more than 0.02 per day. So our two statements might be, one, that it's less than or equal to 0.02 seconds, and the other would then be that the mu time is really greater than 0.02 seconds. Now, because this is the less than or equal to, this will be our null hypothesis, and this will be our alternative hypothesis. We want to see whether or not the true mean time is actually greater than 0.02. Because of that, we are looking for something greater. That means that we're going to be looking here. This is what we would call a right-tailed. Because our alternative, we want greater than, this is going to be a right-tailed. Okay. Let's take a look at another one. A report claims that lung cancer accounts for 25% of all cancer diagnoses. Okay. So we have P is equal to 0.25, and therefore the other one is P is not equal to 0.25. This one will be our null. This one will be our alternative. Okay. And then because our alternative is a not equal to, that means this is going to be two-tailed. Okay, we're going to be looking at something like this for our distribution. And remember, these will be, the only reason I do this Z1, Z2 is if we were working on a chi-square, but in our means and our proportions, then those will be the same. They'll just be one on the lower end and one on the higher end. Okay. Okay, let's keep going here. If P is less than alpha, okay, then we reject the null. If we end up getting a p-value of 0.02 and we're using an alpha 0.05, then we would reject the null in that case. Okay. If instead of getting a p of 0.12, if we got a p of 0.12, notice this is larger than our alpha, we did not get a value that was more extreme than this. Okay, so therefore we would fail to reject. And you've heard me say that a number of times. You never actually accept the null. Okay, that's pretty important. Never accept the null. All we're ever doing is failing to reject the null. Okay, we never say like, hey, look, we have evidence that proves the null is true. No, we don't. We just have our evidence doesn't allow us to reject it. Okay, so keep that in mind. Here's a nice little chart that's going to help you with your wording. Okay, and remember earlier how we would always identify which is the claim. If you claimed H not or H null is true, that was your claim. If you end up rejecting it, then this is the language you would use. There is enough evidence to reject the claim, the blank. Okay, and then you would accept the alternative. Okay. Then if your claim is that this is true and you fail to reject, again, this is where you'd say there's not enough evidence to reject the claim. That's all. If your claim is that the alternative is true and you end up rejecting the null, there is evidence to support the claim that blah. Or if you claim the alternative is true but you don't have enough evidence, then you would just say there is not enough evidence to support the claim blah. And you got to put in your context. Okay? So here, a report claims that more than 40% of households in New York County struggle to afford basic necessities. Okay, so what we want to do is how would you interpret a decision that actually rejects the null hypothesis? How would you interpret a decision that rejects the null? Then we're going to interpret how you would interpret if something failed to reject. Notice we don't actually have any of the data. This is all just practice with rejecting and failing to reject. Okay, so I got the chart here so that we can come back and reference it. Okay. So let's first identify what our hypotheses are so that we can answer this appropriately. So it says a report claims that more than 40%. Okay, so one of these is going to be P is greater than 0.40, and ultimately that's what the claim is. And then the other one will be P is less than or equal to 0.40. And this one's going to be our null, and this one will be our alternative. Okay? So what about if something rejects the null hypothesis? If we end up rejecting the null hypothesis, if we get evidence to say, look, we can reject that. So we can come over here to our chart. Remember, our claim is for the alternative, and we were able to reject the null, and so that means that we would say this one right here. Okay, that's what we would say. There is enough evidence to support the claim That's horrible. Wow. Not a perfectionist, but that was just really bad. To support the claim that more than 40% of households in a New York county, this is long, I should have typed it, struggle to afford basic necessities. There. Okay, that's our part A. Our part B then would be, what if instead it says, what if it failed to reject the null hypothesis? Okay, so what if it failed to reject? In other words, we kind of have to keep this. It's not that we could get rid of it. We have to keep this one. And it's kind of like, if we're keeping that, we also kind of have to think about getting rid of that one, right? But if you look at our language over here, and I apologize, just a little bit ago I said we never accept the null. In some classes I teach with some books, we write these in slightly different ways. But if we follow this chart, you're going to be just fine here. Okay, so notice that in this case, our claim is still the alternative. So this one's our claim. And this time we actually are going to fail to reject. And then if we look and see where those cross, then this is the language that we're going to use. Okay? So if we do that, then we could say, following this language right here, we would say that there is not enough evidence to support the report's claim that more than, I'm going to keep going here, more than 40% of households in New York County struggle to afford basic necessities. Okay, so that would be our language for this one. To review, here's what we're looking at. This is the steps that we're going to go through, and I know this is a long video. There's a lot to it, and once we actually start doing these in the next lesson, these will go pretty quick. Okay, but You're going to first state the claim both mathematically and verbally. Make sure you understand it. Identify the null and the alternative hypothesis. You're going to specify the level of significance that you want. Remember, it's kind of like your confidence level. So you might use like an alpha 05 would be a 5% chance of producing a type 1 error. Then you're going to determine the standardized sampling distribution and draw its graph. Okay, so the standardized distribution, remember, has a mean of 0 and standard deviation of 1. We're going to draw the graph, and then we're going to shade the area, calculate the test statistic and its standardized value, put it on your sketch. Find the p-value, right? And then is the p-value less than or equal to your level of significance? You know, if it is, then you're going to reject the null. You found a number that when you get a really tiny p-value and it's smaller than your alpha, you reject the null and go through and state things very carefully. If your p-value is not, then we're going to fail to reject the null and make sure that you write an appropriate statement. Okay? Now, sometimes it depends on what you want to do. The strategy that you're going to use in hypothesis testing is going to depend on whether you are trying to support or reject the claim. Okay, because you can't use a hypothesis test to support your claim when your claim is the null hypothesis. Okay, that goes back to that wording. As a researcher, you're going to perform a hypothesis test where the possible outcome will support a claim. So word it so that the alternative, I read that very awkwardly. As a researcher, to perform a test where the possible outcome will support the claim, word it so that the claim is the alternative. Okay, if that's what you want to do, you want to actually support the claim, then you are going to make your claim as the alternative hypothesis. To perform a hypothesis test where the possible outcome will reject the claim, then word it so that the claim is the null hypothesis. Let's look at a quick little example of what you might do with that. Okay. So an internet service provider, an ISP, is trying to gain advertising deals and claims that the mean time a customer spends online per day is greater than 28 minutes. You're asked to test the claim. How would you write the null and the alternative hypotheses when you are representing the internet service provider and you want to support the claim? Then that means that what we're going to do is we're going to make the alternative, so we could come down here and say this, we could say the alternative is that mu is greater than 28. Okay, if we want evidence to support this claim, that will be our alternative. And if that's the alternative, we'd come back here and we'd say the initial is that it's less than or equal to 28. Because if we end up getting evidence and then we can reject the null, then that's going to make this a true statement. Okay, so this is for part A. Now, for part B, what if you were representing a competitor and you want to end up rejecting the claim? If you want to end up rejecting the claim that it's greater than 28 minutes, in other words, kind of like making them look bad, calling them liars, right? Then what's going to happen here is we're going to say the alternative is that mu is less than 28. Okay, and then what we would say is that the initial, or the null hypothesis, is that it's greater than or equal to 28. This way, if we end up getting evidence against this and we can reject the null, then we will have to accept the alternative, that mu is actually less than 28. Okay, so notice that these are kind of written a little bit differently depending on what you ultimately want, like what your goals are for this particular who you represent. So keep that in mind. Go back and check this out again if you want. And I know there's a lot of information here. You guys can do a quick Google search on hypothesis testing, and I'm sure you can find videos that cover all this probably in 5 or 10 minutes and give other examples. So I would strongly encourage you to go through and check out some other people as well. As always, read your book. It's a great book. You guys should definitely spend a little bit of time looking that over. So I hope this was a little helpful. Maybe watch it again or find some other videos that might help. All right.